results from the computer calculations. So this the introduction to the four phases called this is the idealized picture for uniaxial lematics. When you the molecule are often thought of as having the shape of the ellipsoid, and they point in the same. They tend to point in one direction. When they form into layers in the uniaxial smectic, the molecule form into layer, but they still point into the same direction. And then we have prediction of the biaxial lemmatic phase about 40 years ago, where this is the idealized picture of this phase, where in addition to the ordering of the long axis, the molecule also tend to order their shorter axis, and they can also form into layers, which we call the biaxial smectic A phase, where they form into layer, but the long axis is parallel to the layer normal. And experimentally, the biaxial smectic phase is found in very few systems, and there's still much debate about the experimental evidence for the biaxial lemmatic phase, but we actually have more evidence for biaxial smectic A phase, and it's almost conclusive. So that's why we develop a very simple model for biaxial smectic A phase, which combines the theory for biaxial lemmatics and uniaxial smectic. And the theory we develop is a simple molecular field theory, where you have just a single particle and interact with the mean field. So the starting point of to introduce the theory is the Meyer-Saupe theory for uniaxial lemmatics. So here you have an order parameter which describes the ordering of the phase, which is an integration with a single particle distribution function. And P2 is a second rank Legendre functions of the polar angle theta, which describes the orientation of a molecule with the directors. So, and this distribution function then depends on the order parameter, and the T star is temperature scaled in the non-dimensional units. So next, to describe the biaxial lemmatic phase, we need 4 order parameters. So we have the P and C in addition to S. So P and C, when they are non-zero, that means this is a biaxial lemmatic. And now we have these functions which are the function of the Euler angles. So we have the zenithal angle in addition to the polar angle theta. And the distribution function now depends on the 4 order parameters, the temperature, and we have 2 biaxiality parameters. And actually we can reduce this order parameter set into 2, and in the literature there are there are 2 models which we can do it. So we call one the geometric mean approximation, and the other approximation developed by the Sonnet, Vierge, and Duran. And these are the two phase diagram from these two approximations. So the difference is in the SVD approximation we have the tri-critical point, and so I should say the continuous line means is first order transition, and continuous line means second order transition, and so broken lines is all second order transition, and continuous is first order. So in the SVD approximation we have the tri-critical point and the triple point, whereas in the geometric mean we have it's called the Landau point. So their qualitative behavior are slightly different, but you can see they have there are some common features. So for uniaxial smectic phase, there's a theory by Macmillan, and this theory has three order parameters. The S in the Maya sulfate, tau is the density wave, and this one is the modulation of the angular dependence of the molecule. So as you can see, actually in this theory the integration is taken over two variables, and we can use this approximation by Covenso-Lucas and Zildi to decouple the angular dependent and the spatial dependent part, and thus we can write these two order parameter as integration over just one variable. So this is the phase diagram, which is not has the same qualitative feature as the original Macmillan theories. So now we can combine the theory for biaxial pneumatics and uniaxial smectics to form our theory. So this theory has been developed by Teixeira, which they have in total 9 order parameters, and the integration of the average is taken over 4 variables, which is quite hard to do calculations. So we can simplify this by using the decoupling approximations, and just now we can write the modulation in terms of the orientational order parameter and the pure positional order parameters. And thus we have just 5 order parameters, and now the integration is integration for f is over 3 Euler angles, and integration for tau is over this the spatial variable. So we can also simplify it further by using the geometric mean and the Sonnet, Vierge, and Duran approximations. And in each case, you have one positional order parameter and two orientational order parameters, and that gives us a system of nonlinear, 3 nonlinear equations to solve. So this is a set of representative phase diagram for the geometric mean approximations, and you can see as we increase the smectic interactions alpha. So alpha increase as the flexible chain length of the molecule increase. So as we increase alpha, then the smectic phases become more stabilized with respect to the nematic phase, and eventually they take all space of the nematic phase. And especially for the biaxial nematic phase, the region is shrunk a lot by increased smectic interaction, just a little bit. So this is for the sonnet Viegas-Durand model, and you see the same features here, and the NB phase disappear even earlier, even for smaller alpha. So I try to get the approximate phase sequences for the two model, and the yellow shaded region means that it is the region where the biaxial nematic phase can be stabilized. So you can see they are stabilized in a very small region of the parameter set. And so the conclusion of my talk is that the biaxial nematic is stabilized in a very small parameter space, and for larger parameter spaces, smectic phases are preempting the NB phase, so that's why it's difficult to find, and the NB phase is very rare. So, but actually in the experimental system, the biaxial smectic phase are found to have a bilayer structure, and the biaxial phase have anti-ferroelectric order. So in future work we may include this effect. So this set of reference I use, and thank you for your attention.
Thank you for keeping time, and we have time for some questions.
For conventional pneumatics, I would expect that there are two uniaxial phases, rollate and oblate, sandwiched by biaxial phases. Might be you said, but I did not find it. So for your case, you always mention only one end view or smectic view. Never.
Okay, let me go back. So for this geometric mean approximation, then you have the if you increase gamma, then this behavior it repeats itself, and so it becomes a disk-like molecule. But there's in this model there's a reflection symmetry, so we only need to consider one part of.
Okay, and for smectics, for biaxial smectics, it's always smectics along long axis of your brick, so might be there are situations when smectics modulation along short axis. Just bricks, line and plate.
Yeah, I think that might be possible. But,
any other questions? Is anyone trying to explore to find these elusive pneumatic biaxial with colloids? Because with colloids you can actually make the prisms, and you can make this Rayleigh model much more, and you can use polydispersity to penalize the smectic.
I don't know.
I mean, they're probably not ready
Colloids,
to
right.
displays,
Yeah.
but
we have the phase in the lyotropic system.
yeah, but that's in my cellar. It's in self-sending. Okay.
In thermotropic, I think maybe the large molecule and the experimental evidence more conclusive. large molecules like it's called tetrapole molecules.
Mhm.
But I don't know if they found it in colloids.
Uh-huh. Any other questions? Or if there are no further questions, I think we can break for coffee. And we thank the speaker.